Welcome everyone to this webinar. Today, the topic of the webinar is a smooth introduction to groundwater modeling using FEFLOW. So my name is Carlos Rivera. For those who doesn't know me, I'm the Global Pro Specialist for FEFLOW DHI. Today, I'm gonna give you introduction to FEFLOW. So it's a really introductory webinar, but I still will show a number of things which might be interesting even for people who has already worked with the software before. So we start with a introduction, theoretical part with PowerPoint, then we will have a live demonstration. Okay, so for those who doesn't know the brand Mike or DHI, so you might have heard about Mike. Mike is our family of softwares related to different aspects of the water cycle, from groundwater and porous media, FEFLOW, the topic of the presentation, wastewater treatment plants, MyPlus for urban water systems, MySheet for integrated catchment hydrology, among others. Today's presentation or webinar is related to FEFLOW. Again, for those new, with FEFLOW, you can simulate a multitude of groundwater processes involving flow, contaminant transport, also reactive transport, groundwater age, heat transport for geothermal applications, all of these processes under fully or variable saturated conditions. FEFLOW is an old software, so existed already in the late 70s, developed originally by BASI in Germany. And then at some point, BASI was acquired by DHI. So we are now DHI BASI, and we have been developing the software intensively in the last years, having 2 releases per year. So in about a month, a bit more, we will have a minor release of FEFLOW, A0 update 2. And later this year in November, there will be another release called FEFLOW A1. So we are now in the FEFLOW A0, where we name it as the next generation of groundwater modeling. This is a major release since the 2015, because we expand a lot our capabilities in terms of conceptual modeling, capabilities in terms of fixing or correcting 3D data from geological models. We have a better integration with wells, with a well manager editor, and we also support some cloud computing in FEFLOW and FEPS GUIs directly. So again, those news to FEFLOW. FEFLOW is a software which we try to make it very easy to use, so you can master your groundwater projects in a daily basis. Powerful at the same time and comprehensive. We will see in the demonstration that we can easily build box models and then also do complex regional models, working with geological faults and any other complex data. FEFLOW is more than just a groundwater software, because we solve a multitude of transport processes or sub-transport processes, of contaminant transport or heat transport. We also solve variable saturated flow, the Richards equation in 3D. This is something that we are even currently working nowadays to improve this, to have a even better performance in the Richards equation. We have methods to compute the groundwater age, exit probability, or lifetime expectancy. We can simulate density affected flow, density driven flow for coastal aquifers or brine aquifers or injections, chemical reactions, and more. So all of these physical process comes with a number of numerical techniques that we use, starting from unstructured meshes in 2D or 3D, different numerical schemes and solvers. So we have a number of solvers that we support: parallel and serial solvers, direct solvers, iterative solvers, algebraic multigrid solvers. The interface is professional. You can customize it. It supports a number of complex visualizations in 2D and 3D. For those working with calibration or uncertainty quantification, we have a direct link to PES, classical PES, but also the new PES called PES++. FEFLOW licenses comes always with a dedicated technical support. We have a number of academy programs that I'm going to show you at the end of the presentation. So free content that you can just register in our website and then get easily new training to the latest FEFLOW technologies. And if you work with the previous, with other software like ModFlow 6, we even have the possibility to easily import this information and create a basic mesh for getting started. So the software is defined in a number of modules. So you layer one interface. If you want to activate mass transport or heat transport modules, you basically need to activate some checkboxes. So you don't need to really change to match the interface. The whole idea is that you layer one software for flow, mass, and heat transport, and the software is smart enough to tell you what parameters you need to define. The software is also defined for local and regional scales calculations. We have everything one single concept, so no different packages. So if you want to do seawater intrusion, or if you want to do reactive transport, or you want to do simple contaminant transport, so you don't have to always choose the packages. We have everything in one interface that try to plug all the different equations as a one single compartment. The interface covers all the tasks: modeling setups, simulation, evaluation of results during the simulation and after the simulation, and we handle everything under one file format. The interface is smart. It provides you some hints if you don't remember, so what is this auction, or if you see a large imbalance in your budget panels, the software will tell you with tooltips some potential reasons of this or explanations. You can personalize the interface and do a number of things, which is nice for your daily operations. So basically, we have a number of possibilities how to build models in 2D or in 3D. So we will see today in the live demonstration just building a box model, so importing or drawing a geometrical domain in 2D. You can just mesh it and then work with this, set your boundary condition, material properties. You want to advance this model to 3D, so we have a method called layer configurator, where you can just import your number of layers or slices, then interpolate inside these widgets, and then add the different geological information that you require. If the geological settings are complex, so you might have some faults or geological pinch outs of the layers, you can also use other techniques in the software to create partially or full extraction meshes. In the release A0 that I was mentioning before, we reactivate significantly our development efforts to handle 3D super meshes. So these 3D super meshes is a 3D representation of your conceptual model, which is built from a number of 3D files, which could be shed files, AutoCADs, or any file format supported by FEFLOW. But also could come from a geological model. Maybe you work with LeakFlow or GeoModeler 3D or GoCAD. We can read this data, import this 3D representation, and then build a 3D supermesh. So in this release A0, we have the possibility to correct this data, repair the data that might come not properly from these geological models, with the intention to increase the chances to generate a final 3D structure mesh. I will show you also a few things that we are working and will be publishing a month from now. So the possibility to even draw directly in FEFLOW faults or 3D information. So if you have a surface, you can build a bounding box and just create a domain from there. Once you have a model, the model might want to represent some historical data. So you come to the question of calibration. We have this tool called FEPES, which comes with every single FEFLOW license. It doesn't matter what license you have, you always have access to FEPES. And this allows you to solve the so-called inverse problem using PES or PES++. FEFLOW has a number of visualization techniques, quite powerful for 2D and 3D. So you can simply draw lines and then do a cross-section or just generate a plot where you show, for example, the pressure or the water level along the line. It's quite practical. You can do animations. You can do 3D visualizations, clip your model, and then look inside. Even if you want, you can export this information as for working with virtual reality. So these are some examples of visualizations in FEFLOW. So all the licenses in FEFLOW allow you to this, and also this, so the convenience import and export possibilities if you work with multiple file formats. So we can handle 2D or 3D data. So if you work with GIS files, like shed files or points, polylines, and polygons. It can be easily imported in FEFLOW. If you have point data and you would like to create a continuous surface for your topography, so we have some methods to interpolate, kriging, invert distance, Akima, etc. If you work mainly in the civil infrastructure domain, so then you will be more familiar with CAD formats coming from AutoCAD or Civil Engineer 3D. So you can also work with this. Or if you have a geological model, which, as I said before, this can be imported into FEFLOW, and then we treat the information as a 3D. Some companies have maybe multiple colleagues or employees working with different parts of the model domain. Maybe there is some specialized people in on the geographical information system. Maybe you have databases which can be used for multiple purposes, not just for FEFLOW. We have the possibility to create links, connections to this database, pull the data, use the data as a part of the model configuration and preparation. And if there is an update in the database, you can retrieve the data one more time and update your FEFLOW model. A lot of times you want to, when you start working with FEFLOW, you feel that maybe you can even do the things faster, which is possible. We have the so-called open programming interface in C++ and Python. And nowadays that Python is really popular. Many of our users are working with these interfaces. We keep developing more of these interfaces, and this is something that it's really worth it to say. So we have this open programming interface already since more than 20 years. And since then, we have been improving these interfaces. You can manipulate parameters, set get parameters, set control boundary conditions, calculate values. And you can do a lot of things with this. So you can embed and use a number of Python packages and maybe do some post-processing or even provide certain interaction of your FEFLOW model for your client. So that is a number of possibilities. And then let me jump to the second part of this presentation, where I would like to show a few things about applications with FEFLOW. For multiple aspects, hopefully some of these will draw your attention. So when we talk about FEFLOW, the major question then comes is regional groundwater management. So we have a number of applications can be solved with FEFLOW, like artificial recharge, for example. So you can simulate your recharge pools and then in FEFLOW model the unsaturated zone and then evaluate how is the wetting from propagating through the bottom zone and whether this is recharged properly the aquifer. River and bank infiltration. So something very common, especially here in Germany where I'm living, river bank infiltration. So you can locate your wells close to river banks and then use FEFLOW to optimize the amounts coming from the river and the other coming from the aquifer. You can use this. You can optimize these quantities, for example, with our H problem class, which will directly tell you the water origins defining a specific well capture zone. Dewatering systems, drawdown assessments, so all of these processes can be simulated with FEFLOW, quite simple interaction with surface water. You can model something simple directly in FEFLOW when you know already the water levels. The software will give you the possibilities to interpolate these water levels along a lines or along your river networks. But we also have more complex solutions. So recently we published a new coupling in 1D between My1D, our new engine for surface water calculations in 1D with FEFLOW. And we also have a coupling for 2D surface modeling. So we have the possibility to couple MIC21 flexible mesh FM with FEFLOW in cases where you want to simulate flooding events or really large extensions, and so you can put this data in MIC21 and then FEFLOW will get the information and simulate the extension of your flooding. Mine water management. FEFLOW is also very popular in multiple aspects in the mining sector, and especially in the part of mine water management. So when you want to solve the question of dewatering, so you have an open cast mine or underground mine, and you would like to dewater this system, so you can work with FEFLOW to get these pressure distributions and also your dewatering volumes. You can optimize this schemes, locations of wells. You can combine it maybe even with pests to move locations of wells and try to solve this with via the inverse problem. You can do a lot of risk analysis assessments with FEPS. What is going to happen if I decrease the pump rate 50%, or it's going to increase my pressure at that level or not? And for this, so the major advantages of the software are the possibility to build unstructured meshes. So here you see in this graph a model, a DHI model, which was built many years ago. Sorry, this one, the lower one, many years ago with layer-based models. So the model was quite heavy because we need to refine it a lot in terms of layers and in terms of elements, triangles. And then at some point, we were asked to update the model, and we rebuild the model with the new meshes, with unstructured meshes, which give us the possibility to add more details in the area of interest, in this case, the area of the open cast. And in those areas where there are part of the area of interest, I could significantly increase the size of the elements or the volumes of the elements laterally, but also horizontally. Water quality is also a big part of the FEFLOW business. So we have a number of users working with FEFLOW for solving a number of water quality challenges, from seawater intrusion in coastal aquifers. So you can simulate intrusion into a coastal aquifer. Do some risk analysis, what's going to happen, for example, if this contaminant arrive this point from A to B. So if I have a contaminated aquifer, how I could use some remediation techniques to minimize this risk. We have also, back to the mining point, a lot of FEFLOW models happening also right now in the context of lithium and potash mining in multiple places of the world, especially in South America, Australia, and the USA. Nuclear waste storage. So it's in DHI, currently we have a large project investigating nuclear waste also in Germany. So FEFLOW can be used for all of these different tasks because we solve the most simple advection, diffusion, dispersion equation, but we can also extend these capabilities by adding multi-species transport, which means that you can have a number of species solved in parallel, which could be interconnected through equilibrium reactions or non-equilibrium reactions. Even if you think you need to do more complex geochemical calculations, we have the possibility to link this via Frixie. And on top of that, you can always add viscosity-dependent, density-dependent flow, mass transport or mass reactive transport in fracture flow, and so on. Geotechnical and porous media, will go quickly on that to move to the live demonstration. So this is related to all the different aspects on pore water estimations, pressure distributions, maybe estimation of leakages, seepage through dams, levees, and other cases where there is significantly change of the saturation. We solve the 3D Richards equation in FEFLOW. We can parameterize this with a number of empirical methods, Bang & Nochten, Bruce and Coley, and so on. And this helps us to answer a number of questions. And the last section of this applications is the geothermal part. Due to the energy crisis in these years, so we see a significant use of FEFLOW by our customers in different aspects of geothermal modeling, shallow geothermal, but also in deep geothermal. In terms of geothermal, you can simulate with the software open loop system, but also closed loop systems, so-called BHE, borehole heat exchangers. So the software will tell you propagation of heat or temperature in the system. So what's going to happen if you work with this specific amount of energy or power in the system. If you have a number of boreholes, you can also connect them and then treat them as a one single array. But there is always more, and more is the amount of information that we provide with the software. So we have online help, which is continuously being developed and updated with every release that we have. We have a number of exercises, tutorial videos, white papers, which come with the software. If you would like to get a more information from the mathematical background of FEFLOW, you can also buy the FEFLOW book if it's necessarily. We have a program called the Academy by DHI, which develops a number of FEFLOW trainings, online training, classroom training, self-paced and instructor-led courses with our own data, standard DHI training, but you can also customize the training. If it might happen that you have data and you want to start with FEFLOW, we can also set up a tailored training working with your own data, which will help you to speed up the learning curve. So I would like to mention that we have also a number of free self-paced training courses, which are trying to cover multiple aspects of the modeling with FEFLOW. You just need to register to this. So I will show you the link or paste the link in the chat for our Academy website. You can see that we try to cover the full spectrum of application with the software come from groundwater flow. So we have introduction to FEFLOW. So if you really did not start with FEFLOW at all, if you want to start after this webinar, you can just register to this and then you will learn basic things, how to create meshes in FEFLOW. Have a course, introductory course about mass transport. Heat transport, we just published last week a second part of a geothermal course. So we have open loop systems and closed loop systems. If you're working with complex geological data, if you have a geological model and you would like to integrate this into FEFLOW, we have a new course just published also last month about advanced modeling of complex geologies, where I show you how to integrate this data into FEFLOW and repair the data. And if you already work with FEFLOW and you would like to do the things even faster, you have a full training course, again, for free, related to FEFLOW and Python APIs, where you can learn how to access data, run the simulations, do a scenario analysis, do calculations of budgets, change boundary conditions, and even do particle tracking without opening FEFLOW, just with a Python script. We have a FEFLOW community very active. This is the link of our FEFLOW forum. We have a quite number of interactions in between different communities from different countries talking and asking about groundwater modeling. We also organize regular national and international meetings and conferences in different topics of groundwater modeling or in FEFLOW. And as I was mentioning before, part of a good reason to acquire FEFLOW is the technical support, which is really dedicated to help you and support you with all these different questions, either technical questions about the FEFLOW interface, but also regarding the theoretical background. And with this, I would like to jump to the online demonstration. So we have, so let me open another NT interface first. It's on the other screen. So when you start with FEFLOW, the first thing that you see is you have a number of panels. These panels are can be organized in different locations. So you can customize your layout if you want. First thing, you want to create a project, file new. And then I was showing at the beginning of the presentation that you have a number of paths or routes to create a 3D model or a 2D model if it's needed only. Let me take the simple path, starting with a 2D. Next, and then even simple, I want to draw the domain manually and just need to press finish. Then comes this window called Super Mesh, where you define your conceptual model. Your conceptual model entails what is the area that you would like to model and what are the geometrical features that you need to solve your modeling task. Maybe you want to simulate rivers, so you will need to digitalize here some lines, wells with points, and different polygons representing material regions and so on. So FEFLOW works with basic geometries, so polygons, lines, and points. You can use all these different entities to draw any system, so you can just draw it or provide coordinates if you know them directly. So I'm gonna build easily a box of 1,000 by 1,000 meters. We have here, so that's my domain. That's my domain. This domain needs to be discretized because we are solving a finite element problem at the end of the day. You have a number of generators, so we can add some wells, some points here to define the wells. I can choose triangle mesh generator, which is most of the commons mesh generators for finite elements. You can control the size of your meshes. So you can just press generate mesh, you have a mesh. You don't like it if you want to get better details. So I would like to maybe have some discretization around the wells. So let's say here some values. So these control refinements of points. And then if you see below, then you have a better discretization. So you can do this as many times as you want. It just takes you a second to create a mesh. This is a simple mesh. Even if you have something more complex with number of polygons, lines, etc., it will be very fast. So let me say, okay, maybe this is too big, so I can generate it 50 meters, and then that's what's it. Let's find something in between. And now we have a little bit of discretization. So you can always come back and change the value. So these values, there is no rule of thumb for this, but it takes you quite some time to get experience on the parameter, but it's quite easy to try. So normally I work with such a gradations of between 3 and 5. Okay, so you have a mesh. The mesh it has a proper quality. You can check the quality of the mesh if it's required through this auxiliary data. You can look angles, so we look for equilateral triangles. As, if you think it's an appropriate mesh, then you move forward to the next step, which is basically create or define what you want to do with the software. You go to problem settings, and then there is the center of FEFLOW where you control the different options. So either it's a horizontal aquifer, it's a vertical cross-section, maybe you want to simulate a dam. Maybe you're doing a pumping test where you consider isotropic conditions, so you can solve this by a vertical axisymmetric projection. It's a standard flow, steady state. Let's do it like this. Yes, and start reading questions in between. Somebody's asking me if it's possible to model the Badow zone. Yes, you can, for example, say vertical, and then if you choose Richards, you will be able to model the Badow zone. So the unsaturated zone as also is named. Okay, so I have this steady state. We have boundary conditions. So we have always 4 types of boundary conditions: head, flux, fluid transfer for simulator rivers mainly, or surface water bodies, and well VC. So we can set some boundaries. The philosophy behind FEFLOW is that you need to choose a parameter. By double click, I did this in hydraulic head, then create a selection of, then define some values, and defining the hydraulic head of 30 meters on one side, and on the other of also of 29.85 meters. So I have a natural gradient, a regional gradient. I can also define material properties. Is a confined system. FEFLOW is tell you that you require a transmissivity. If you are going to choose unconfined before, then FEFLOW change this list of parameters and doesn't ask you for transmissivity. It will ask you for conductivity. So I choose the parameter, then say I would like to have a global value of 170 square meters per day transmissivity. I can save the model, and so add here some demo, and then run the calculation, and we have something very simple, which is a distribution of hydraulic head. Nothing very special. I can see the gradient from left to right. So I can now start perturbating this by adding boundary conditions. So I can put 2 wells because we measured these 2 locations. You can manually select the location of the wells, but you can also use maps like points here, and then use this information to create a selection. You have marked these points, and then you can define boundary conditions like well VCs or others. So I'm gonna put 500 cubic meters per day pumping here in these 2 locations. Maybe I would like to also add some groundwater recharge on top, which is called source scene parameter in FEFLOW. Again, we need a selection to define could be a constant, could be heterogeneous. And then I give a value of recharge in the system. And now we can run the model again and then see what's happened with distribution of hydraulic head after we start perturbating. So now I have a drawdown here being caused by these two wells. You check the solution of heads, looks for me plausible because I have a gradient, I have a drawdown here. You will need to check the values. And second step, you need to control the budget. So we have a number of panels for this. One of these is called rate budget panel, and this rate budget panel, I put it here on the middle, give you the overview of all the different flags. So we have a Dirichlet VC. This corresponds to the heads left and right. So I have a positive in green, so it's water is coming into the aquifer. I don't have fluxes, I don't have rivers. I have two wells, 500 times 2, 1000. I have recharge constant value 510 to the minus 4 meters per day was what I added times the area, which is 1000 by 1000 meters, give me a total recharge of 500 cubic meters per day. Because we simplify the reality with a discretized system with the finite element method. So there is always an error. This is called imbalance. So every software, doesn't matter which one, always has an error. And this imbalance in FEFLOW in this case is 410 to the minus 8. What do you see the units cubic meters per day compared to the other components? You can come out to a conclusion that this imbalance is a negligible factor or value for this domain. So therefore, FEFLOW has closed the water balance. So that's just a simple exercises to get started with the software. If you want to know more and see all these step by step, I would recommend you to join the first self-paced course, which basically build this model together with you and give you some theoretical background about these different workflows and options that I'm using in FEFLOW. Also, what is a good mesh? So how do you check the mesh quality? You will learn all these different. Okay, so let me open some other model that I have prepared here. The model has a number of boundary conditions, so I can put the boundaries. This is a model that we use for our training, our commercial training that we for teaching FEFLOW. So we have a river here on the middle. We have some inflows and left, north, south, and a number of pumping wells. On the right side, you see these blue dots. They correspond to the sea borders. So the head is constant and 0 meters. You can also add some tidal information if you want. This is a steady state model. This time I'm solving unconfined conditions. As I was mentioning before, FEFLOW requires transmissivity. So I have some patches of transmissivity being added already in the system. How do you put this data in FEFLOW is quite simple. You can import maps which contain the data. So I have, for example, this called land use. This could, or in the case of the conductivity, I have this one, matprop. If I look the map, this is just a set of polygons. And the whole workflow is through this so-called parameter association, where you link information from the outside world. From a map file, could be a shed file, an AutoCAD file, point data, line data, doesn't really matter. You link it to a parameter, and then you tell FEFLOW how to migrate the data from left to right. In this case, since it's a polygon, basically just look elements which are inside the polygon, but you could have something more, something different. Let me see if I have some. This one, for example, elevation. So I can also tell FEFLOW, this is point data. I have a list of points containing elevation. I'm telling FEFLOW, look, this data from the left has to be linked to this parameter on the right side and use interpolation called kriging. So you can define your own settings and define this. So if we run the model, it just takes you 1-2 seconds, it's done. The model, we have now different components. So we have a different distribution. So we have a discharge from the aquifer to the sea. You remember the boundary here of the sea level. So this is represented at this. We have some fluxes, inflow, north, south, left. Then the river is in and out. We don't know what is happening in the in and outflow. We could investigate this. We have pumping wells. we have some recharge zones, and then there is an imbalance, which is a bit higher compared to the previous model, but still is very small compared to the other water components. So if you would like to investigate the connection between the rivers and the aquifers, what you can do is quite simple. You can plot the river first. We have FEFLOW works with what we call selection. So we can store this selection. So this is my river. And I can tell FEFLOW use this selection, which is the river lines, to plot some information. In this case is the budget information. So what I see here on the panel, I could also see it in space. And it's here now. So now we need to set some settings about display. So I'm gonna ask to change the legend here. We can deactivate this. And now you see some, maybe this is a little bit bigger, trim. So you have a number of little spheres or circles which represent the budget at each of the nodes of the river. So positive inflow, so means the river is recharging the aquifer, and negative means the aquifer is exfiltrating back to the river. So you can define this. You can also look the connection even farther. So you have wells, so we can again create selection of this and say this can be called wells. And we can do now particle tracking and see the hydraulic connection between the different elements. So now I have some particle tracking, which requires a number of properties. This is something that is also explained in the self-paced courses, if you want to look on that. And now we can draw the capture zone of each of these 9 wells. Then you can see wells are interacting with the river, but also getting water from the inflow zones. So this might be in conflict, these 2 wells. This is basically extracting directly to the river, it's hydraulically connected. You can verify, you see here yellow is an inflow. So the river is recharging the aquifer, and the capture zone of the well are really connected to the river. So whatever is infiltrating from here might be captured by the well. Okay, that's this second exercise. And the third one is let's go to 3D. And I will try to show you this in 5 minutes so that we have some questions for answering, some time for answering the questions. So I have prepared some data. This exercise is part of something that what I showed the last month, which is available in our website as well. And we have a section called on-demand webinars, which are some of the best webinars that we have, are very interesting. So we record it and we make it available. So let me add this file. So this file it's a domain. The domain can be defined by a set of surfaces. You can build the surfaces by your own. In this case, I did this with Python, but you can also import a geological model, and then you will have the whole block of information. So I was telling you that we are working in these workflows. So in the current FEFLOW, you can import maps and then convert these maps into what we call super mesh elements. So let me add some folds, for example, here. So I can say this map has represent a fold, and then I can add the fold into the system. So that's nice because you can add it and always change your information depending if you are getting more hints or insight of geological model. You can do something even easier now with FEFLOW. Let me go remove this one. Remove it. In 1 month, we are releasing some more updates of the software, and we have the possibility to even build these folds inside the software. So we have add 3D super mesh plane, so you can digitalize, you can provide, if you press F2, FEFLOW is going to ask you the coordinates, so you can draw the path of your fold. You can provide the angle of orientation. So let's say it's a positive 45 degrees. What is the mean and the maximum elevation? I just draw one. and then you can have it. So I didn't change any settings, just drawing the fall or the surface higher. With the options that we implemented in the A0 and with a new module that we call FEFLOW Advanced, you have the possibility to repair this data. So if you're gonna mesh this, it's gonna complain that there is an error because the data is not fitting. So it cannot be that the fall is outside your topography or your base of the model. But we can throw it away, the parts that we don't need it, by calling the super mesh repair, which basically it's gonna get rid of the data, fixing potential self-intersections or intersections with geological inputs in 3D, which don't fit well or not at all. It's gonna take a few seconds most of the time. Okay, so the model is being remeshed, the fall, and now I can create a mesh out of this. If I just mesh it here with, so, and now the mesh is done. That is another type of mesh. It's called unstructured mesh, and creates the implementation of the fall here. Okay, but I would like to not spend much time on this and maybe concentrate now to the questions, because this is a little bit more advanced. If you want to know more about these workflows in 3D, again, I would recommend you to take this course here, 3D modeling, advanced modeling of complex geologies. So with this, I would like to thank you for participating in this webinar. Don't forget to join our newsletter community. You will receive the information of these webinars or different free training courses if you are part of this FEFLOW community newsletter. The next month, we will have a webinar. We always have a webinar the third Thursday of the month. The next topic of the webinar is already available. All the next topics are already available in our website. So you can register and then get the material or participate in the webinar. Even if you think that you will not make it on time to the webinar, I recommend you to register, because you will always get the material if you are officially registered in the webinar list. Thank you for participating, and I hope to see you the next month in the next FEFLOW webinar. Thank you. Bye. Until the next time.